Math, we picture that good old equal sign, right? One thing equals another. But let's be real. Life isn't always about perfect balance. It's usually full of comparisons, like, are you going to have more than 3 scoops of ice cream? You think you can get this done in less than an hour? Did you really watch at least 2 seasons of that show last night? See what I mean? Life is rarely perfectly equal. So today, we're going to learn the language to describe all that other stuff. So let's step beyond that familiar equals sign and explore the much, much bigger world of comparisons. An equal sign is great when 2 things are exactly the same. But what about all the times they aren't? That's where inequalities come in. They are, at their heart, just a way to compare 2 things and figure out their relationship. So if you want the official textbook definition, here it is. An inequality is just a mathematical statement that's comparing 2 values that aren't necessarily equal. It's all about showing their relative size, who's bigger, who's smaller. All right, so now that we know what we're talking about, let's learn the actual language of comparison, the symbols that make this whole thing work. Believe it or not, it all starts with a super simple symbol. It kind of looks like a sideways letter V. But this little shape, it's way more powerful than it looks. This guy right here is the less than symbol, and I'm going to give you a fantastic trick so you never ever forget it. The small, pointy end of the symbol always points to the smaller number. It's a perfect little visual clue. And on the flip side, we've got its partner, the greater than symbol. The best way to remember this one is to think of it like an alligator's mouth. The big, open mouth is always trying to chomp down on the bigger number. So let's just put them side by side for a second. With less than, the small point goes toward the smaller value. With greater than, the big open mouth faces the bigger value. That's really it. Once you get that down, you have totally cracked the code. Okay, now for the really fun part. Let's take these symbols out for a spin and use them to translate some everyday, normal phrases into the language of math. Here's a perfect real-world example. Imagine someone setting a fitness goal. I want to work out less than 5 days a week. How on earth would we write that using math? Well, first things first. We need a placeholder for that thing that can change. You know, the number of days someone actually works out. In algebra, we call this a variable. For this, let's just use the letter W to stand for the number of workout days. And now we just put it all together. The phrase workout less than 5 days turns into this simple, elegant little inequality. W is less than 5. And just like that, we've translated from English to math. But, you know, writing it down is only half the story. The really cool part is when you can actually see what the solution means. So let's try to visualize it. So we have our inequality. W is less than 5. But what does that really look like? I mean, what are all the possible answers? Is it just 4? Or maybe 3? What about 4.5? Or 1.2? Well, check this out. This number line isn't just some line with numbers on it. It's actually a picture of every single possible answer to our inequality. It represents working out 4 days, 3 days, 2, 1, 0 days, all of it.
Now, it's really crucial to understand the 2 parts of this graph. See that open circle on the number 5? That's super important. It means 5 itself is not part of the solution because the goal was less than 5 days, not 5 days or less. And then that big arrow pointing to the left covers every other possible number that is a solution.
And that's really the magic of it all. Unlike a simple equation that might have just one single answer, inequalities give us a super precise way to talk about a whole range of possibilities. So, to wrap this all up, I'll leave you with a little challenge. We've all been there. You look at your phone and you see it has less than 20% battery left. Using everything we just talked about, how would you write that as an inequality? You know, in math, we're so used to getting that one perfect answer, right? Like x equals 5. But what if the answer isn't just one number, but a whole range of possibilities? Well, that's the world of inequalities. And today, we're going to figure out how to draw a picture of a whole bunch of answers all at once. So, let's start with a question. How do you actually draw an answer that's everything less than 5? I mean, it's not just 1 point on a number line. It's 4. It's 3.2. It's -1,000,000. It's a huge infinite set of numbers. So how do you possibly capture all of that in one simple drawing?
That's the puzzle we're going to solve.
All right, our first tool in the toolbox is what we call the open circle. This is what we pull out when we're dealing with a really strict boundary. So let's look at this expression. W is less than 5. What this means is that W can be any number you can possibly think of, all the way up to 5. But it can never, ever be 5 itself. 4.99999 is fine, but 5? Nope. Off limits. And here is what that looks like on a number line. See the shaded arrow? That shows all the possible answers stretching off to the left. But look closely at the number 5. See that circle? It's empty. It's hollow. That's our open circle. And it's basically a big visual sign that says, hey, 5 is the starting point, but it is not included in the answer. So let's just lock this in. An open circle simply means not included. I like to think of it like a fence. You can walk right up to the edge of the fence, but you can't sit on it. The number with the open circle is the boundary, not an actual part of the solution. Okay, so we've handled those strict rules. But what happens when the rule gets a little more generous? What happens when we add just one tiny line to our symbol? Now, check out this symbol. It's our less than sign, but now it's got a little line underneath it. That line is basically half of an equal sign, and that's exactly what it means, or equal to. So now our expression reads, W is less than or equal to 5, and that tiny change means 5 is now officially part of the solution club. So since or equal to is now in the game, we need a brand new symbol. And this is where the closed circle comes in. It's a solid filled-in dot, and it means the exact opposite of the open one. It's a loud and clear signal that says, yes, this number right here, it is included in the answer. Okay, so now we have our two signals, the open circle for not included and the closed circle for definitely included. Let's put them head to head and really see the difference in action. Just look at this comparison. On the left, we've got W is less than 5. On the right, W is less than or equal to 5. The number line looks the same. The arrow is shaded the same way. Literally, the only difference in the entire picture is that one dot on the number 5. On the left, it's open, so 5 is excluded. On the right, it's closed, so 5 is included. That one decisive dot completely changes the meaning of the entire graph. So really, it all boils down to this. No line underneath the symbol, you use an open circle. That number is not included. If it has that little or equal to line, you use a closed filled-in circle. The number is included. That's the core rule, right there. All right, I know what you might be thinking. This is all great for a math test, but why should you actually care about open and closed dots? Well, it turns out you use this logic every single day, probably without even realizing it. Think about it for a second. A speed limit sign says your speed must be less than or equal to 65 miles per hour. That means 65 is totally fine. That's a closed circle. To get on a roller coaster, your height has to be greater than or equal to 48 inches. If you're exactly 48 inches tall, you're good to go. Another closed circle. From movie ratings to store discounts, these rules define the boundaries of our world all the time. So we started with a simple question. And now you know how to visualize a whole world of answers on just a single line. You've learned the visual language for infinite possibilities, and it all comes down to that one decisive dot. Now that you've got this tool, what other math challenges are you ready to solve?